Okay, guys, so today I want to talk about genetic drift, which is a topic that comes up pretty often in the discussion of evolution. So, what exactly is genetic drift? It is a mechanism of evolution. It's a way that evolution occurs. There are many ways, and this is just one of them. Um, and genetic drift is dealing with allele frequencies and how they change over time or over generations because of chance. The alleles that you deal with when considering genetic drift are typically neutral, meaning that one is neither dominant or recessive, and they both have equal chances of being passed along, which is one of the key aspects of this because it's all related to chance. No one allele has a better chance um, of being passed along more so than the other one. The parameters for genetic drift are finite population size. So when you have an example with genetic drift, your population is not going to be enormous. It's actually usually going to be pretty small. And low migration rates. You don't want new alleles introduced to the gene pool because that will throw off the frequencies. And the results of genetic drift are a reduction in variation, and one of the alleles will become fixed while the other will become eliminated. And it's an odd uh, mechanism of evolution because typically when you think of evolution, you think of increasing variation, but this actually does the opposite. Variation is reduced, so it's considered a weak negative evolutionary force, while most others are considered positive or stronger evolutionary forces. So the fixation and elimination aspects, what exactly do those mean? Fixation is simply when the frequency of an allele reaches 1, and elimination is when the frequency of an allele reaches 0. So when you are in a population and the conditions are favorable for genetic drift to occur, of course, you've got your homozygote individuals and your heterozygote individuals. Genetic drift will pull the frequency of either your A1 allele to a frequency of 1 or your A2 allele to a frequency of 1, and the other allele will be eliminated. So to make that a little more clear, let's move on to an example. And I made this illustration. It's a smaller population size than I would like to work with, but genetic drift usually occurs in small population sizes, so it will work. There are 40 marbles. We're going to call them marbles. That's what they are supposed to be in this bucket. And 20 are red and 20 are blue. So if you were to draw 10 marbles out, and those marbles are going to represent the viable adults in the population who choose to mate and reproduce. So if you draw out 10 marbles randomly, you're going to get allele frequencies, and those allele frequencies could be 50-50, and those would be ideal conditions. So you could get 5 blue marbles and 5 red marbles, but there's also a possibility, since this is random, that you get other numbers like 7 blue marbles and 3 red marbles, or blue alleles and red alleles. So this is a good illustration of how genetic drift occurs, because in a small population, only a portion of the alleles will be passed down to future generations. Subsequently, the future generations probably won't be a perfect representation of what that initial population was. And eventually, under genetic drift conditions, one of those allele frequencies will continue to skew to an extreme, yielding the expected results of genetic drift, which are elimination of one allele and fixation of the other. Sorry, my PowerPoint isn't responding. There we go. So let's go over some numbers associated with genetic drift. So if the alleles are neutral, meaning one is neither dominant nor recessive, and they have the equal the equal ability to be passed on, and N represents the population size, then the average time to fixation is 4N generations. Also, the chance of fixation of an allele is proportional to its initial frequency. So, like in our previous example with the blue dots and red dots, the bottom figure had 7 blue dots, so the blue allele would have a 70% chance of going to fixation, while the red dots would have a 30% chance of going to fixation. And that's inversely proportional. If it's got a 70% chance of going to fixation, there will be a 30% chance of. So let's move on to a little math. Just using that first fact that we learned, the 4N generations formula as the average time to fixation for one of the alleles. Let's look at some real numbers. If you have a population size of 2,500 individuals, how many generations would you estimate before one of the alleles is fixated? So simple math, you just multiply it by 4 because 2,500 is your N. So that would be about 10,000 generations before fixation of an allele. Same with the rest of the numbers. 1,000 population size would be 4,000 generations. Population size of 100 would be 400 generations. Population size of 10 would be 40 generations. So there are our expected generation numbers. I want to introduce you to a simulation website that I find very interesting in visualizing some of this information. So it's called RedLinks. You can either follow the link in the PowerPoint or Google RedLinks simulation and it should come up. But if you follow that link, it brings you to this website and you just start your simulator and it brings up a chart with the frequency of allele A1 in the population. So you have a lot of values to adjust down at the bottom, and if you'll remember our parameters for genetic drift, the migration rates are low. So we're just going to be using ideal conditions. So we're going to drag that down to 0 to work with genetic drift. So some of the numbers that we're familiar with, I'm going to start with the smaller numbers. Let's just start with a population size of 10. And we'll set our scale, this is just adjusting the x-axis, we'll set our scale to 100, and that is because we expect 40 generations until the allele A1 is either fixated or eliminated. So we will just click Run Simulation, and that is surprisingly a very nice graph of exactly what we would expect. The allele went to fixation right at 40 generations, which usually doesn't happen. I've done this several times and I'm a little surprised. But all that said to say, one data point we know as good scientists is not enough. So I want you to run the simulation multiple times and get an average. So see, this time the allele frequency was eliminated at 20 generations rather than fixated at 40. And it's moving a little closer to 40, but just click a lot and see what it comes up with. And it's interesting to see that this is indeed completely random. It's not formulated. You can't guess exactly where any specific line is going to go because genetic drift is also random. No one allele is more dominant than the other. And this is a good representation of that. So if you were to increase your population size, just pick a random number. Let's do 30. We're going to assume that 30 times 4 is 120. So after 120 generations. So we want to see maybe 200. Run simulation. And it eliminated very quickly. And the more times you click, the more data you will get. And some of these are kind of closer to what we would expect. So if you wanted to affect things like what we talked about in the second fact in the PowerPoint, that was to do with the frequency. So our blue allele was at 70%. So let's try that. Let's go back to good, clean numbers like 10. And we will expect about 70% of the time the A1 allele, we're going to call that you could relate it to the blue allele because we put it at 70%. It doesn't really matter what you call it. We're going to assume that it will go to fixation about 70% of the time. So if you just click, if you counted, you would probably get pretty good data, but it's just a good representation. It's a fun way to see visually some of the data that we talked about, some of the numbers. So the last thing that I want to leave you with is a connection to real life. How do scientists use this? How can I apply this to life outside of the classroom? And that real life connection is conservation biology and endangered species. So when population numbers within a species that happens to be endangered drops below certain numbers, there's a threshold, then the effects of genetic drift become very evident because there are not enough alleles in the population to maintain that variation that is needed. And there's a lot of research that goes into this. And if you just Google conservation biology and endangered species, it comes up with some pretty interesting things. And that's just something you might want to look into to relate this topic back to real life. But that is all for my video on genetic drift. I hope you enjoyed it and I hope you learned a lot. Thank you so much for your attention.